Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This is a second video in a series on the introduction to graphing using calculus. In the previous video, we talked about how to determine intervals of increase or decrease of a function, and we talked about the increasing and decreasing test. Now, we're going to talk about the first derivative test and how to use that to find local extrema for a given function. We'll first start with a simple visualization. Now, if you watched the previous video, you already probably kind of gathered what I'm about to say because, well, it's somewhat obvious, but we talked about the fact that if your derivative is negative, your function's decreasing. If your derivative is positive, it's increasing. Notice that we just went through a local minimum. Remember, a local minimum occurs if you have a point, f of, in this case, negative 1.5148. That point is lower than or less than or equal to, the y values less than or equal to all local y values. So notice this is the lowest point locally. It's not the lowest point on the graph. Oh, I guess it is. All right. It is. This happens to be the lowest point on the graph, but it doesn't have to be, okay? It just happens that I'm looking at the lowest point on this graph, but it doesn't have to be. It just has to locally be the lowest to be considered to be a local extreme or a local minimum in this case. But notice that our derivative went from being negative to positive at that point. So if your derivative switches from negative to positive at a point, you have a local minimum. Now, technically, we're only going to say this for a continuous function. So if you have a continuous function which switches from being having a negative derivative to a positive derivative at a point, you will have a local minimum. If your function's not continuous and it switches from negative derivative to positive derivative at that point, it is not necessarily a local minimum. So continuity is required. I'll give you an example of that in a moment, but let me go over to this guy right here. This is a local maximum, right? It was climbing, we get to the highest high, and then it falls. Notice the derivative is positive because you're increasing, and then the derivative is negative because you're decreasing. So you went from a positive derivative to a negative derivative. That should imply to us, for a continuous function, that we have a local maximum. Now, all of that stuff that we've just kind of mentioned is going to lead to a theorem, but I just want us to recall before we move into that theorem, Fermat's interior extremum theorem. If f has a local extreme, which is what we were looking at, local minimums and local maximums, and if the derivative exists, then the derivative at that point, at that local extreme, should be zero. So that is an important theorem. It is the converse of that is not true. So in other words, if you have a derivative being zero, it does not mean you have a local extreme. But the way it's written here is true, that if you have a local extreme and the derivative exists, then the derivative at that extreme must be zero. That being said, that grows into the first derivative test. The first derivative test says if we have a critical number. Now remember, a critical number is a number such that, is a number c, such that f prime at c is equal to 0 or f prime at c does not exist. Well, I shouldn't say equals because that'd be a weird way of saying it, but just does not exist. So that's what a critical number is, just as a recall. So supposing you have a critical number for a continuous function f, and that continuity is incredibly important. And I'll give you an example of why it's important in a little bit. But if f prime changes, the derivative changes from being positive to negative, and I don't know what's going on with my screen, there we go, at some number c, then f has a local maximum at c. Again, you have some function, its derivative is positive and then negative, where it switches from positive to negative derivative, you have a local max. If f prime changes from being negative to positive, then you have a local minimum. If f prime doesn't switch signs at that point, then f does not have a local maximum or a local minimum at that point. A good example of that is something that might do this. It flattens out momentarily and then continues on. The derivative right there is 0, but it is not going from increasing to decreasing. It's going from increasing to increasing. Therefore, it's not a local maximum, nor is it a local minimum. Pretty easy to understand, I hope. We're not going to prove that theorem, mainly because it's kind of a simple theorem to prove, and most textbooks kind of cover it. So let's go ahead and do an example here. Find all local extrema of the function. Now, this function we actually dealt with in the previous video, and our work from that previous video is going to apply here. So each step of the way, we're growing our work. And you can even see I copied even my note that a critical number is where f prime is 0 or f prime doesn't exist. Just to remind you, we needed to find the critical numbers. So we solved f prime is equal to 0. And we found out the derivative is 0 at 0 and at plus or minus the square root of 2. Then we built a sign chart for f prime. And we said, okay, f prime is positive from negative infinity to negative root 2. It's negative from negative root 2 to 0, and you can see the rest there. And that implies that your function's increasing on that first interval, decreasing on the second, and so on and so forth. Using this information, I can easily use or find all the local extrema using the first derivative test. The first derivative test tells us if our function's continuous, which our function is, then our function reaches a maximum if a local maximum, that is, if our derivative, our function switches from increasing to decreasing at a point, or in other words, our derivative goes from positive to negative at a point. So our function went from increasing to decreasing at negative root 2, so negative root 2 must be a local maximum for our function. Then our function went from decreasing to increasing at x equals 0. So that, if it's going from decreasing to increasing, that must be a local minimum. And then it went from increasing to decreasing. So it went from increasing to decreasing at the square root of 2. That must be a local maximum. Again, these are all by the first derivative test. So this is how you would use the first derivative test. You would take the first derivative and then you would, well, test, right? So f prime is changing between positive and negative at negative root 2. So therefore it's a local max, and so on and so forth. It starts to become more of a natural feel as you build out these problems. And it becomes easier for you to tackle these as we move on. This leads to our improvement on our recipe list, I guess. Given a function f, accurately graph. Well, again, to begin to accurately graph, we're going to take that first derivative, determine the intervals of increase and decrease by finding the critical numbers, and then use the first derivative test to indicate the local extrema. Again, the first derivative test just says if your derivative changes from positive to negative, you have a local max. If it switches from negative to positive, then you have a local minimum. Organize the information and graph. And again, that statement about organizing the information and graphing is me basically saying, look, draw a number line. That really will help you out. Trust me. Now, often I'll have like synthesis questions for a different video, but I really didn't want to create a separate synthesis question video. So we're going to include some of those synthesis questions here, mainly because there's just not enough of them to merit a video on its own. So suppose that f and f prime are continuous everywhere and have the following values. Well, okay, f prime has the following values. So at x equals 0, our derivative is negative 5. At x equals 5, our derivative is positive 5. At x equals 10, our derivative is 1. And at x equals 15, our derivative is negative 2. Based solely on this table, where can we guarantee local maximums and local minimums? Well, if you think about this, the critical piece of information here, two critical pieces, that f and f prime are continuous, specifically f prime, that is very important. F prime being continuous for this table is important because then I can use the intermediate value theorem. F prime went from a -5, remember f prime is continuous, it went from a -5 to a +5. So that means somewhere between -5 and +5, the derivative had to become 0 because it's continuous. And so therefore, there's some point between x equals 0 and x equals 5 where our derivative switches signs. So based solely on that information, we can easily see that our derivative goes from being negative to positive. In other words, we'll have a local minimum. Notice how I always draw that, by the way. It's just a fast way for my brain to say, oh, negative to positive local min. So we'll have a local min, an L min, if you want to call it that, occurs on the interval somewhere between 0 and 5. X equals 0 and 5. Now let's look at the next group. So our derivative, again, that's the second line, goes from a value of 5 to a value of 1. Well, we can't say anything is going to happen as far as local mins or local maxes between x equals 5 and x equals 10 because our derivative didn't change signs. It might have, but we just don't know. This is such a coarse piece of group of information. In other words, it's not finely detailed enough. We don't have like all the x values between 5 and 10 represented. So maybe our derivative became negative, but we would never know based upon this table. So we can't say anything there. But let's look at the next pair. Between x equals 10 and x equals 15, the derivative, which is continuous, remember, goes from a value of 1, which is positive, to a value of -2, which is negative, obviously. And because our derivative is continuous, the intermediate value theorem tells us that going from a positive to a negative for a continuous function, it has to cross 0. So there's a point where our derivative is going to be 0. Our derivative went from being positive to negative, so therefore we must have a local maximum somewhere between x equals 10 and x equals 15. So we have a local max on 10 to 15. We don't know exactly where, but that's all we can say from this table. So this is a good style of question that could be asked by your instructor or maybe in your homework or something like that. So just be aware that those can be asked of you. As a final example in this video, let's just go ahead and ask ourselves kind of a theory question. The function f of x equals 27x plus 4x to the -2 has a derivative that is positive on the interval -2/3 to 0, and the derivative becomes negative on the interval from 0 to 2/3. So let me give you a visual of this. The derivative is positive, so you have some increasing function from from -2/3 to 0. And then the derivative is negative from 0 to +2/3. Now, I'm not claiming that this is the actual graph of this function, so please don't assume that I'm saying that. I'm just saying that this is a visual of what you might think it looks like. But then I'm also telling you, f doesn't have a local maximum at x equals 0. So how does this not contradict the first derivative test? I'm telling you, f does not have a local maximum at 0. I promise you it does not. So how does this not contradict the first derivative test, which is this test right here? Well, the critical piece that we need to know or need to consider is that our function has to be continuous to even begin discussing the first derivative test. And if you recall, the function we're dealing with, which is this guy right here, that function actually is not continuous. That's not continuous at 0, in fact, because of that x to the -2 power. So this function not being continuous at 0 means that we wouldn't even be able to begin to apply the first derivative test. So let me write that down. And just to showcase what the actual function looks like, it's a function that looks like the following. It has a vertical asymptote there. And it looks like that. It's increasing on one side of that vertical asymptote and decreasing on the other side. But it's not, the function's not defined at 0, so therefore it does not have the opportunity to have a local maximum. So that little word continuous, which is part of that theorem, the first derivative test, is one of the most important words in that theorem. You need a continuous function to even start considering the use of the first derivative test. That being said, I want to reiterate something I mentioned in the previous video. I don't technically call these theorems by their names, and so I will often not state, oh, and by the first derivative test. I will just say, listen, we've got a function, a continuous function, its derivative switch sign, so we have a local max or a local min. I don't really call it the first derivative test. It's more of a natural or a heuristic method for me. All right, so that does it for this video. I'll see you in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.